I'm going to try recording this to the cloud. Morning, everyone. Today is August 18th, 2018. That would make it 8/18/18. And this is the John Chappell Natural Philosophy Science Chat. And let me bring up my presentation here. Now I'm supposed to be able to share my desktop here. Okay, so I've got my welcome page here. Let me put all this stuff aside here. Okay, so welcome everyone. And this is, of course, sponsored by the CNPS. And you can visit our website at naturalphilosophy.org. You can join and renew your membership. And we can be found on Facebook. And we have our own wiki. And we are on social media. So if you are on social media, give us a like. We can also find and subscribe to our videos on the YouTube channel, where you will find recordings of the science chats. So hopefully we have something new every week for you there. So check it out, and you can see the other old recordings there as well. And we also invite you to help us out. We're trying this new thing called Basecamp, and you can find that at hq.naturalphilosophy.org. And you can help us out, volunteer to help us do things like this science chat or organizing our information. Okay, so this is just going to be an open discussion today. So we were discussing a little bit about Bill Lucas's work here, so I think we can continue that discussion a little bit here. Now, last week, unfortunately, we couldn't hold the science chat because Bill seemed to have an unexpected power outage, so we had to cancel that particular meeting. I think later his power came back on, but not before we could notify people that that was going on again. And Bill also had some technical problems with restarting the meeting we had set up. So there are a couple problems. So maybe we'll have to have Bill come back and represent what he was going to be doing, which is something on the fundamental force, which is his book. But we were discussing here when he was on here last time about whether there was this book by Poincaré about meta theory, right? So, who was speaking about that? Is that Bob or? Okay, you guys can go ahead and unmute yourself and get back in conversation.
I was trying to find out what the title of Poincaré's book that contained that meta theory, and was hoping Bill would be here or answer an email, or maybe he sent it to you, a title, so I could chase that down. But so far, no luck.
Well, we could always do some research here live and see whether we can find out ourselves. So, Harry, do you have any other clues for us as to what to look for here? Now, you mentioned that you found a list of all of his papers. Maybe we could go look at that, first of all.
I found on the web.
I suggested that you look up meta theory, Poincaré meta theory on the internet. And if you really are, and if you want to find out whether there are any books that have been, Google Books or Google Scholar is a good source of information on that. I suspect there is no book.
Yeah, I
Okay?
suspect there's
I suspect it's
probably...
buried in some other book.
Well, if we just look here, then how do you spell Pointier? P-O-I... Anybody know?
Poincare.
Okay. Well, let's see if I got that right. See, now
You gotta go to Google Books.
Here is one of his fundamental books here, The Foundations of Science, Science and Hypothesis, the value of... See, this is like something that might have fish theory in it.
You're not doing what I told you to do.
All right.
The Poincare's got a lot of stuff. You're just going to get, meta theory.
All right. So we got his name right here.
No, wrong.
H. Pointier. Okay, so where should we go, Harry? Are we going to go to Google Books?
Poincaré meta theory. Google Books or Google Scholar.
Okay, let's go to Google Books. Books, google.com. Okay.
All right, now when you do this, you're going to get a lot of hits from places where it refers to Poincaré meta theory.
Yeah,
it looks for two words.
Uh-huh.
Remember when you were supposed to sit too close to the screen? And video games were anti-social?
So let's see. We found this other book that was already there, The Foundations of Science, Science and Hypothesis by Henry Poincaré.
Network is ready. No matter what VR, 8K, 3D entertainment the world comes up with. Are you ready for that?
Value of Science. International Conference on Theoretical Physics.
What's going on behind the scenes right now today?
We couldn't do this without the best reporters.
So probably, whatever it was, it could have been in any of these. But still, that doesn't bring us to a title that we can go after.
What it does is it goes and it looks through and finds where you have the words Poincaré and meta theory in any textbook. So now you have to go through all those sites and look and see whether anything is relevant. Kind of the hard way to do it. But you see, there's no book titled Meta Theory by Poincaré. Okay?
Nope, there isn't. So, I mean, this is the interesting thing here. So they found, like, the word meta theory in one of his writings here. But it's not terribly common. I mean, it doesn't look like meta theory is a term which is commonly used by Henry Poincaré himself. You would see. That's why it's a little bit hard to find things on it. So we'll just have to wait for Bill to see if he can provide us with the title.
What you
need
to do is you need to go through all those citations. You need to go through all those citations that come up and look and see what the hits correspond to. Okay, some of those textbooks, some of those refer to authors who are discussing Poincaré's meta theory.
Yep. Although the thing is, that still wouldn't help us.
There's a bunch of background noise. I can't really hear.
Yeah, there's a bunch of background noise. Now, it could
Science
be
and
that
hypothesis is...
From my perspective on this investigation, I think when I was first going, before we got to Rudy Giuliani.
We're just going to have to wait for Bill to tell us, because if there's no obvious title that you can look up in the internet, I'd say would be our conclusion here, Now, it could be that this book has been so banned that that's why we can't look it up in the internet. That, you know, that's why we have to ask them.
There's no book. It's probably a part of some other book.
Probably, but that's not Bill's claim. Bill's claim was that there was an actual book that he could not check out.
Well,
on meta theory. So, but we're just
that was probably more because the book was in the incunabula, or the restricted section where they have. The other issue is that it could be in French, which is another problem.
Yeah, we got a lot of noise from Peter Parker, so I muted you off. Okay, well, so that, I think that will conclude our discussion about whether we could look up this mysterious banned book, but I don't think we can. So we'll just have to go back and
there is no banned book.
But
there is no banned book, and if it was banned, we wouldn't be able to look it up on the internet now. That seems kind of obvious.
Ah, well, maybe. So that's the other hypothesis. But the thing is that so these things that happened to Bill happened to him like 30, 40 years ago. So he may have troubles recalling the exact natures of those kind of things.
Well, to move things along a little bit, I came across a quote that I thought would be interesting to read here and to get people's input on. Any chance I could have the display?
Theoretically, I'm going to stop sharing and let's see whether there's any control on your side. Like there is I can see in the bottom of the screen that there's like a little share icon. Yeah, you're sharing. Okay. There you go. We can see that.
Okay, so here's a quote from Einstein's 1905 paper on the electrodynamics of moving bodies. In fact, it's the first paragraph of that paper, and this is the HTML or the address where I got the translation from. Here's an interesting quote. Interesting to me, has to do with classical electrodynamics. That's what I'm primarily interested in and primarily researching. Here's what Einstein wrote. It is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. The observable phenomena here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. For if the magnet is in motion and the conductor at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy, producing a current at the places where parts of the conductor is situated, or are situated. But if the magnet is stationary and the conductor in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force to which in itself there is no corresponding energy, but which gives rise, assuming equality of relative motion in the two cases discussed, to electric currents of the same path and intensity as those produced by the electric forces in the former case. End quote. I find that very interesting because of the asymmetries that he is pointing out. And in my research in electrodynamics, I trace that back one of the asymmetries anyway in electrodynamics. I trace that back to the definition of current. See, the definition of current in classical electrodynamics seems to be just the charge density rho times the velocity of the source only in the arbitrary coordinate system chosen from which to measure velocities and positions and so forth.
So can we just go back and clarify what was being said there?
Sure.
So to me, so that's saying that if I hold a magnet in my left hand and a wire in my right hand, you're saying that if I wave the wire around, I see a voltage being generated on the wire, but if I hold the wire still and wave the magnet in my left hand that I don't, is that the asymmetry?
Well, the asymmetry is in the way that it's being described. You see, Einstein is writing here, the observable phenomena here depends only on the relative motion of the conductor and the magnet. Okay, so you can hold the magnet still and move the wire, or you can hold the wire still and move the magnet. The phenomenon is the same. Okay.
So
however, he's saying, however, the customary view draws a sharp distinction between those two cases. Not the phenomena. The physical phenomena is just the relative motion between one and the other. But for some reason, the physics description of it distinguishes between the two cases, whether the magnet is stationary or whether the magnet is in motion. And I'm saying that I think that is because, in part, of the way that current is defined in classical electrodynamics.
Well, I'm saying I don't understand at all what that means. I mean, you're saying it's the same,
Nobody
but it's different.
else does, Franklin, so you're not alone.
I mean, what is he saying here? That
Who is
doesn't
it
make any
that's
sense to say
talking?
it's the same
I don't
and
know
it's
who
different.
is talking. Who's
So I
talking?
want someone to explain that to me.
Well,
Because you're not going to get anywhere
Who
until
is
you
it that's
explain that.
talking?
this is Bob Gray.
Okay, Bob, are you the one talking?
I just recited or quoted this paragraph from Einstein.
So
I think that's
what is
yes.
the difference
Bob.
here?
Yes.
Bob,
I mean, as
Go
far
ahead,
as
Ray.
I know, both cases generate an EMF at the wire, right? So what difference are you talking about?
This.
You know, we're going to have to stop trying to talk at the same time.
Well, there's too much delay. Let me explain this.
Please go ahead.
Let me explain it.
Go ahead.
The reason for the asymmetry is because of the Maxwell theory that is based on the ether. And in the Maxwell theory, it is the motion of the magnet that creates an electric field in the ether. Okay? And that is where the asymmetry comes from, because in the one view that the electric field is created in the ether, okay, you get an asymmetry from the other point of view, which is the electric field is created in the circuit at rest. And you need to read the reason that, and this is very controversial, because if you read different books on Einstein's theory, there are different interpretations of what he says here. Okay? And so even the establishment people in the physics community don't know what this means.
That's
No,
correct.
that's terribly confusing. But what I'm hearing you say, Harry, is that basically the electrodynamic theory predicts an asymmetry, but we don't see an asymmetry.
No. the asymmetry results from the theory of the ether.
Yeah, so that's a particular hypothesis. So
Okay, so what
the
I'm
ether
trying
hypothesis.
to say,
I mean, I'm just trying to figure out
let
what's
me
the
say
nature.
this again. Let me say this again. What this is leading to is saying that the ether doesn't exist, because if you base your electrodynamic theory on the ether, you get this asymmetry which he's talking about here. So in other words, the ether theory of electrodynamics produces an inconsistency. So he then uses this as an argument to say there cannot be any ether.
Right. I would go in a slightly different direction. I don't disagree with you, Harry. But let me see. There's something else here.
Yeah, just click no on that. Hal, you clicking on something?
See, I think in part this paragraph is saying that there is no asymmetry in the physics of the phenomena, but there is in the description of Maxwell's electrodynamics of that phenomena. And
If you assume the existence of an ether.
And I'm suggesting part of why there is an asymmetry in the Maxwell's electrodynamics is because of the way that they have defined current. They define a current only of the motion of the source charges. They do not consider in the definition of a current the motion of the detector or the test charge particle. The way I conceive it is you have source charges and a test body which can, feel the force of the moving source particles. And their definition of current only has the motion of the source charges. It does not have the relative motion between the source charges and the test charge.
Well, I don't see any test charges here. I see a magnet and a wire.
Hang on. There's your test charges.
What does that mean?
So I have a source charge on the left, on the bottom, QS, and it can be in motion, and what we want to know is the force on the test charge. So
once again, I don't see the charges.
What do you mean? You don't see my screen? You don't see my screen?
I see your screen, but those are that's describing forces between two charges, and we were just talking about a magnet and a wire. I don't see charges in either of those.
Yes, but we're talking about asymmetry in classical electrodynamics in general, and I am saying that part of that asymmetry comes from the definition of current as used in Maxwell's theory. Current in Maxwell's theory, in part, is made up of a lot of Q sub S's, the source charges in motion abstracted to be a continuous source charge, but let's just take the fundamental, which is a source charge and a test charge. And it's the relative motion between those two which should describe the physical phenomena. But Maxwell's electrodynamics does not have the relative motion between those two charges. It only has the motion of the source charge in the definition of current.
Yeah, but we're talking apples and oranges here again. It's like Einstein was talking about magnets and electrons and wires, and you're talking about two distinct independent charges, and those are apples and oranges. You can't say that any physics from between the interaction of two charges applies anything to the forces, the magnetic forces between a magnet and charges and wires, I would say.
Charges and wires are composed of discrete charges, Q sub s. You could call it Q sub s I if you wanted to add them all up or identify each individual charge. All magnetic phenomena comes from charges in motion. What that motion is, I don't know, but I've never heard of any magnetic field that is not generated by charge in motion. Now, maybe that's my assumption here, but that is why you talk about a magnet, fine. It reduces to a charge or charges in motion. And a wire, whether it's
different force than the electrostatic force.
The point was that I believe that paragraph from Einstein is one example of asymmetry in classical electrodynamics. Here is what I'm saying is another asymmetry, and the reason for that asymmetry. The reason is their definition of current. So I'm trying to broaden it not just to that one example that Einstein is talking about, but a little bit broader, still within the scope of classical electrodynamics.
Okay, so I think I got that. So what is your problem with current then?
The current does not take into consideration the motion of, in this diagram, QT, the test charge in motion.
You might click no on that. Right?
Why not click yes, give somebody else a chance. How do you stop sharing?
So I'm still not quite understanding what you think the problem here is. I'm still getting a pretty good echo here.
Do you recall the definition of current in classical electrodynamics?
My definition of current is electrons flowing through a wire. That's my definition of current.
Okay, we can start from that. So you have a wire. What is your coordinate system? You can arbitrarily define a coordinate system.
The coordinate system of the solid wire.
Okay, so in that, you say the solid wire itself as a whole is not in motion in that coordinate system? That's a question.
Yes, that would be correct.
Okay, then the charges in motion in that wire have a velocity of something, an average drift velocity or whatnot. And you would consider that to be the definition of current?
Yes, I would consider that the definition of current.
Then what about the test charge that you have to use in order to feel a force due to those moving charges in that wire? Okay, that test charge, to feel that force, does not have to be at rest in your coordinate system. That test charge can also move in that coordinate system. And as it moves at different velocities, it will feel a different force. And so what's really important is the relative velocity of that test charge to the velocity of the current charges in that wire, not the absolute velocity of the source charges in the coordinate system only. The definition of current has to take into consideration the velocity of the test charge as well.
Well, I think that you could always consider the velocity of the test charge in the frame of the solid wire. and you could get the velocity off of that. That's the only velocity that really counts.
Well, it's the difference between the velocity of the test charge and the velocity of the current in the wire. That's what really counts.
You could always calculate that.
Sure, but then notice that that is the relative velocity between the test charge and the charges in the wire. That's not the definition used in classical electrodynamics, and that is an example of an asymmetry that I think was being mentioned in Einstein's first paragraph. I would identify that as an asymmetry. Okay.
Everything you just said doesn't make any sense to me at all.
So they can get back to the work.
I mean, everything else you were saying was fine. You got the relative velocity, you've got the wires, electrons going through the wire, the force depends upon the relative velocities. I get all of that, but everything you said after that didn't make any sense at all.
Okay, the first step would be that that is not the definition of current used in the electrodynamic textbooks. They only define current by the velocity of the source charges in the wire. They completely disregard the velocity of the test particle.
Well, how do I know that?
There's no need.
I mean,
because you look in Jackson or Griffiths or any of the other textbooks, and you look up current, and you'll see that it's defined by, for example, the charge density of the wire times the velocity of the charges in the wire with the test particle. There isn't one in that definition. It's in the textbooks with only considering the source charge motion.
So what's the difference if you normalize your velocity to this test charge motion? If you leave the test charge motion at 0, there is no difference. You're just arbitrarily picking the test charge as the test.
Be very careful, because when you say that we can have the test charge velocity equals 0 in the coordinate system that we choose, and you're perfectly right, you can do that, but then look at the force equation, which has the Lorentz force equation, which has a component Q times the velocity cross product the magnetic induction field. What is that velocity? That's the velocity of the test charge, and you just set that to 0. You said the velocity of the test charge is going to be 0, that's fine, but then that component of the force is also 0.
So it's still the difference between the test charge and the moving charge.
The force is different.
I could just as well set the moving charge to velocity of 0, and the test charge is moving relative to it.
Only if you define current as a relative velocity between the test charge and the source charges. If you take out that test charge in that definition of current, then you cannot do that.
You have to pick a frame somewhere.
That's fine. Pick any frame you want.
So how do you measure the velocity of the moving charge relative to what?
Relative to your arbitrarily chosen but fixed coordinate system.
And I arbitrarily choose that fixed coordinate system to be my test charge. What's the difference between that and choosing absolutely any other charge in there? Any other velocity or frame in there?
The difference is, as Franklin is showing, the Lorentz force, that QV cross V, the V, because of the way you chose the coordinate system, is always 0.
Yeah, but it's now increased. Now my velocity of the charge has been increased.
Only if it's Only if it's defined to be the difference between those two velocities.
If both charges are moving in the same direction, then they basically nullify each other. There's no field between them.
Not in the classical definition of current, because current is defined only as the velocity of the source charges.
Relative to a standing still test charge.
Relative to an arbitrary coordinate system.
No,
and
relative to the coordinate system. Relative to the coordinate system that is the test charge at 0.
But then, okay, fine, but then
that's an implied.
But then this V in this part of the equation of the Lorentz force is always 0. QV cross B, if you're saying the velocity of the test charge is always 0 in the coordinate system that you select to use, which is perfectly fine, then that part of the Lorentz force equation goes to 0 because you selected V to be 0 in that coordinate system.
Fine, but the field is still moving past it.
That's fine, but it's not going to feel any force because you set that force, the velocity to 0.
You don't have to have a moving object to have a force.
That's correct. The first term, QE, that does not go to 0. But I'm saying that the Lorentz force term QV cross B does go to 0 because you set V equal to 0.
Well, I don't see another... You only have the magnetic force here. That doesn't mention the velocity of the electrons creating it. See, there aren't two velocities here. You just have a magnetic field. And I don't know that you can give a magnetic field a velocity against a moving charge in that field. That's what the Lorentz force law is saying. So I don't understand what you're saying at all about there being relative charges.
If you look at the definition of B, maybe it's further down, you'll see that that involves the velocity of the source charges.
I don't think so. I mean, in permanent magnets, there's some question as to whether there are, I mean, where is the velocity of, where are the charges, in fact, in a permanent magnet? Well, that's really, I mean, we can see that in like a solenoid, you know. You can clearly see that, but in a permanent magnet, it's like, where are those coming from? I've always kind of speculated that a permanent magnet is like a bunch of coils, tiny coils inside of the crystallization of the permanent magnet, but then you would have to believe that those are like superconducting loops, which is a possibility, but, and generally speaking, even if they did do that, it would be all these tiny little loops. And like, what is the velocity of those electrons going into tiny little loops? I mean, they're going in loops, so they're changing direction all the time. So what kind of velocity can you say they constitute? I would say that would, you know, there's no way you could say that the electron in my hunk of supermagnet is heading in any velocity. I mean, it's rounded out to 0, really, right? But yet it's still creating this external magnetic field. Now, I would say that perhaps the magnetic field itself could have, say, a velocity. If I take my magnet and I just kind of waved it in the air, then it would be dragging around that magnetic field with it, and that could have a velocity. But that's nothing to do with the relative velocity between those electrons in the magnet and your test charge, I would say. Because what Lorentz force is saying, this is the thing that's confusing me, that I can't even quite figure out in my own mind, which is that we have the relative velocity is not between two test charges in the Lorentz force. It's between a magnetic field, measured however it is, and a charge moving through that field. So there's a bunch of vectors running around in here.
Magnetic fields arise because of moving charges. What that motion is, I don't know. That's my hypothesis, but I haven't seen anything that says here's a standing magnetic field that has no associated charge and motion. It just exists. I've never heard of that. I've never seen that.
Well, that would kind of depend. And see, this is the problem, is that we're talking about things where we don't fundamentally understand what, say, the magnetic field is. So it's kind of like...
Bob.
Yeah, go ahead, Harry.
Could you repeat what you just said?
I am
Repeat
not
what you just said.
I am not aware of a magnetic field that does not have charge and motion as the source of that magnetic field. Now, maybe there is. I'm just not aware of that. So whenever I hear magnetic field, I always go back to what is the source of that magnetic field, charge and motion.
Well, that's why I brought up the example of a permanent magnet.
Well, that's pretty much an assumption on your part. Please don't interrupt.
I'm sorry, I didn't hear that. Okay.
You're hearing your own echo.
All right, here's my problem I have, Bob. Are you saying the problem is in a permanent magnet you have a magnetic field but no charges in motion that we know of?
Yes, that would be kind of my counterexample.
But I would disagree with that because all charged particles spin one half, they have angular momentum. Whatever that motion is, and I'm not saying that it's a nice little even circular motion or anything, I'm just saying it has a magnetic moment, it has spin, it has charge, that charge is in motion causing that magnetic motion. Whatever that motion is, I don't know. You add it all up throughout that material and you get a net, what we call magnetic field.
Well, that's all theory. And but let's get back to your fundamental assumption, Bob. You're talking about electrodynamics. Is this not correct?
Yes, that's correct.
Now, electrodynamics is not the same thing as classical electromagnetism. Electrodynamics deals with charges in motion. Okay, and usually refers to TV, CRT tube, where you shoot electrons out of an electron gun, and physics where you accelerate elementary particles and smash them together. That's electrodynamics, right?
I agree with you, but I don't agree with you in the sense of I'm not excluding any electromagnetic phenomena from electrodynamics. But yes, I understand what you just said is perhaps the standard way of viewing the distinction between electrodynamics and electromagnetics.
Okay, let's take the example of I have a CRT tube. Okay, and I'm shooting electrons out of this electron gun in a CRT tube. Okay, why don't the electrons repel each other?
Oh, they do. If they're close enough to, if they're close enough.
Magnetic force.
Yeah, hang on just a minute. That web page you were just showing, can you go back to that? Okay, now scroll up and you'll see a definition of current. Right there, just above the box. J is equal to rho charge density times velocity. That velocity is the, for example, average drift velocity of the charges in that charge density, rho. It does not include the charge, the velocity of the charge of the test particle. And I'm saying that is a cause, one cause, not the only, of the asymmetry in Maxwell's electrodynamics. You need to include the velocity of the test particle there. So it should really be rho, parenthesis, V minus V. One V is the source, the other V is the test charge. Then it's a relative velocity, and you don't have these kind of asymmetries. Anyway, sorry, Harry, that was just something I saw while he was saying.
Is talking about.
Well, it's one because it's magnetism and it's a induced current in a wire. So magnetism being caused.
That's still not what Einstein's talking about.
He's still talking about a magnet, and a magnet is a collection of charges in motion. So you have to go back to the definition of the current, these charges in motion.
Yeah, but all the textbooks don't agree with what you're saying.
Exactly, and that is the reason why they've missed part of the problem that's occurring in Maxwell's electrodynamics. They need to include that relative motion, not just the motion of the source charges.
I mean, that's your main point, right? But they just can't look at the source charge current motion, right? You got the wire, you get the electrons. We only look at the velocity of the electrons through the wire, and you're saying that's wrong.
I think the problem here is that it's a cross product. So basically it's saying that the magnetic field is established orthogonal to the velocity of the electron. And then the force is also established orthogonal to the velocity of the field. And the two orthogonals basically mean the velocity of the test particle doesn't really matter, because what matters is the strength of the field that the other particle is moving through, because the two orthogonals cancel.
Well, here's my point, okay? We're not talking about charges in motion. We're talking about currents measured in loops when there's a magnet in motion. So we're talking about a permanent magnet. There's no hypothesis made about the source of the magnetic field in the magnet. And we're talking about a loop of wire that's connected to a device. Okay, usually, traditionally, it was called a galvanometer. Okay, but basically, it's a meter that measures magnetic field. It doesn't measure current velocity, doesn't measure motion of charge, it measures magnetic field. So what you're measuring is when you move the magnet towards the wire that's coiled up into a coil and is connected to a galvanometer, which is a current measuring device, there is a magnetic field generated, okay, inside the loop, which is detected by the measuring device. And everything is involved in this measurement is magnetism. There's no measurement of motion of charge at all.
Now, that's exactly right, Harry. The test charge is velocity. The original velocity.
Well, the experiment has nothing to do with test charges.
No, the original velocity that created the magnetic field and the velocity of that electron doesn't matter. You're measuring the magnetic field and its source of the field has no significance. The strength of the field and the direction of the field that you're moving to is what matters. And so what you're saying is correct. The charge in motion doesn't make a difference. What initiated the magnetic field does not make a difference, whether it's a whole bunch of charges moving slowly or whether it's a single charge moving extremely fast. You get the same strength of the field. So the velocity of the charge doesn't matter. What matters is the strength and the direction of field. That's what you're measuring.
Well, let's get back to what Einstein was saying. So now that we've got the whole background here, maybe we can go back to your original 1905 paper here and try and make sense of what he was saying, because I'm still trying to figure out. I've got the magnet in my
before we
left hand.
discuss this, Franklin, let me point out that the physics books don't agree on interpreting what Einstein says. So the
Yeah.
experts don't agree on what he said.
Oh, that's clear.
Okay?
So here in the science chat, we're free to think however we like. So we're going to try and figure it out ourselves.
The point is, the official physics books don't agree amongst themselves.
That's right. So we're in good company then. So let's go back and look at the first point, right, that Bob was trying to make here. That is Einstein right or wrong here? You know, I've got the magnet in my left hand and the wire in my right. I move the wire or I move the magnet. Both cases seem to generate electricity.
Franklin.
You said something?
Let me interrupt you here and say that the modern textbooks, there's no problem, no issue, because they've corrected the modern theory of electromagnetism to make it so there is no longer a contradiction, as pointed out in this 1905 paper.
So you're saying they already fixed the problem?
Correct.
So, Bob, what do you have to say to that? I mean, Harry says they already fixed this problem.
They didn't fix it very well. if they fixed it at all.
I mean, that's why we're having this discussion.
Right. Now, I would like to add that if you look in the textbooks on what the magnetic induction field is, the B field, they say the theory aspect is that it's the curl of the vector potential. And then if you look at, all right, what's the definition of this vector potential thing that you're talking about? That is defined in terms of a current density. So the B field is fundamentally defined as a current density. It's, you know, curls of this and cross products of that, but it's still the source of B in all of these classical electrodynamics. Maxwell's classical electrodynamics goes back to the definition of a current density. Now, whether that's physically correct, I don't know. But the theory says B is a function of a current density.
Bob, that's the magnetic current, not the electric current.
It's a current density. It's charge and motion.
It's the magnetic current, not the electric current.
What the heck's a magnetic current? It's charge and motion, but you're saying that there's...
Magnetic current is B.
I think he's saying...
I mean, isn't it true that if you have a wire and you have a current going through it and you just suddenly stop the current, that it takes some time for the magnetic field to dissipate? It doesn't immediately disappear. So that would be an immediate contradiction in that the magnetic field can exist in the absence of any charge movement there, because it takes time to collapse, which to my mind says that the magnetic field is a property of space and not necessarily caused by the moving charges, and could possibly exist theoretically without those moving charges.
No,
well, I
that's
think
not true.
there's...
I mean, Franklin, because the charge is also distributed, so it also takes a while for the entire charge to move. Just because you stop the center of the charge doesn't mean the entire charge pattern is stopped. Charge, remember, is distributed infinitely from the point particle throughout space. So when you stop the point particle, you don't stop the entire charge's motion.
Yes, you do. I don't see how you can say that.
Well, it's a field. The charge is an entire field. Charge doesn't exist just locally as a point.
Yes, it does.
Well, if charge
Absolutely, charge exists as a point.
If charge existed as a point, how could one charge 10 feet away from another charge feel the other charge?
Because it's sending a signal from one to the other, like a radio wave, right?
It's a field. The charge is the entire field, not a point.
No, I would say that the charge is in fact a point. I mean, that's just my feeling. I mean, I could be wrong about that, but that's the way I see it. I see the charge as a point. So in my mind, if I have a battery that's sending electricity through a wire, and I disconnect the wire, that those charges will come to an immediate halt. But yet the magnetic field around that wire does not collapse immediately.
And that's where we'll have to that's where we'll disagree, because like I said, charge is not a point. So we'll just have to leave it at that, I guess.
I mean, even if you thought that the charge is this field, the field would also immediately come to a halt.
No, a particle
so I don't see what the
field.
difference is.
It's like saying if you have a pilot wave and you stop the center of the motion of that pilot wave, that every wave within that waveform stops immediately. That's not true. It takes a while for that reaction to occur through the media that's carrying it.
Yeah, but there's got to be a difference between your pilot wave coming off a moving object and one which is stationary.
If I have a bobber,
and we know that only the moving one is the thing that generates the magnetic field.
If I have a bobber moving up and down on the surface of the water, it creates spherical rings, and if I move that bobber linearly, those spherical rings will move it, but I can stop that bobber's motion immediately, and yet the spherical rings that have already been released continue to move in that spherical expansion plus linear motion. It takes a while for the subsequent spherical rings to catch up and stop around the central point. And that's
okay. Well, I can see where you're going, but my point still remains that I don't believe that that's an explanation for why the magnetic field persists after you stop the motion of the electrons.
Okay, but we are in agreement then that the charge is the entire field, not just a point at the center of the field.
Well, I mean, I can explain that in my own theories, as in that, you know, literally the electrostatic field is being emanated by the point electron as an electromagnetic wave, but I know that that wave does not have anything to do with the generation of the magnetic field.
Yeah,
the magnetic field is, I mean, the magnetic field, in my opinion, is a polarization of the ether particles. So that doesn't actually have anything to do with the electrostatic force coming out of the charges.
Right, and that's kind of where we again disagree. We're going to have to disagree, because, like I said, in my view, a field and a particle is its field. That's what defines the particle, is the field, the energies that it emanates from it and towards it. That's how we identify it, is by its energetic interaction with any other field. So, in my view, a particle is a field. It's not distinct from its field. And in that case, it's like the ring, like the moving pilot ring on the surface of the water. The bobber is not really there. The bobber is just there for us to be able to mechanically create it. But what's really there is the spherical rings. That spherical ring pattern, that is a particle.
Yeah, and I understand that, and I would have to just completely disagree with that. So, and that's okay. That's totally okay. I'm not going to change your mind, and you're not going to change mine. But we just have to understand the various viewpoints here.
Okay, but that's where I'm coming from when I say that when you stop the particle, you don't stop the entire field. It's the electromagnetic field, and the electro part keeps moving as well as the magnetic part, and they will catch up with each other. So that's where I'm coming from that viewpoint.
Well, I don't see how you can explain the way that it falls off. I mean, it does fall off. It does go to zero, right? If you still have your waves going, then it should keep on going, right? That magnetic field just keep on going. But it drops off, so you have to explain why it drops off.
It doesn't drop off. It goes at the inverse square rate forever. It never
And
drops.
it doesn't.
It just gets weaker and weaker. There's no such
No,
thing
it dies. It goes to zero.
So
it definitely goes to zero.
you can have actually two electrons far enough away from each other that one does not sense the other's presence.
That's not true.
Well, that's what you just said. It went to zero. The force goes to zero.
I'm saying the magnetic field goes to zero.
Now, that's not true any more than the fact that the electric field goes to zero.
Hey guys,
No,
I'd like to
totally
get back.
true.
Hello, guys. I'd like to get back to a very important point that was just being raised before this discussion. There's something about there's a different kind of charge and different kind of current. Something about the definition I was using for this B field, this magnetic induction field, is not correct. It's not charge and mode. There's something there, and then we went off kind of on a little bit of a tangent. What can somebody clarify? Is there different kinds of charges?
I don't know that anyone was saying that.
Well, they were saying that when I pointed out that B is the curl of A, and A is a function of the current density, they were saying, oh no, but that's a different kind of current or a different kind of charge. It's a magnetic charge, or it's something, and I don't get that. Can somebody...
I said that, Bob. I said, and I said it's a magnetic current, not a magnetic charge. Charge is strictly electric. Magnetic
There's no
current
such thing as a magnetic current, I don't think.
There is. Look for it. You'll find that magnetic current is described as the B field. And basically,
Magnetic
what that would
current.
be is like if you have a static magnet, a magnet, and you move it along the axis of north-south axis, then you have actually created a magnetic current, because that entire magnetic field is moving linearly, which causes it to be a current.
But that definition
it's
of
the relocation
B...
of the relocation of the center of the field is a current.
Yes, but that B field that's existing before you start moving it is a result of charge in motion. That's the definition of B is equal to the curl of A, and A is a function of current density.
But
I'm not saying that's the physics, I'm saying that's the theory. I'm not saying that's the physics, I'm saying that's the theory.
I think you're looking at the difference
Let me interrupt,
between
Bob.
a current flow and a no, what the heck is it? Just a minute. Go ahead and talk, Harry.
Okay, let's go back to the fundamentals. This guy Ørsted, I'm sure you've heard of him. Okay.
Oh yeah.
And he said, okay, he connected these two terminals of a battery and brought the wire that connected the two terminals of this battery near a magnet, and hence supposedly discovered, okay, the current effect of the electric charge, right? Can we agree to that?
Sure, yes, please continue.
But nobody really knows what's going on inside that wire. It's an hypothesis that current flowed from one terminal of the battery to the other terminal of the battery. But nobody ever proved that. All they did was measure a magnetic field.
I agree with that, and I'd say that, okay, go ahead, fine.
Okay, so if that's your starting point, then to say that there's a current of electrons or something moving called charge inside the wire, that's an hypothesis. That's just a theoretical hypothesis. And then you construct your theory based on that theoretical hypothesis. That's basically all they've done. What you actually measure is magnetic field.
It was shown, Harry, because you were referring to a cathode ray tube before where the electrons are moving freely and they can be detected freely. And they are coming out of the end of the wire and into the end of another wire.
That's a different phenomenon.
It's a what?
That's a different phenomenon.
Well, it's not.
That's a different phenomenon. We're not talking about that.
In order to measure the current flow of electrons in a wire, you have to break the wire. the cathode ray tube is certainly an example of a very easy break in the wire where you can actually see and detect the electrons moving freely. If they move out of one end of the wire and into the other end of the wire when you break it, they are, when you connect it, still moving without the break. So it is shown that electrons...
I didn't... We're not talking about that yet. We're still talking about Ørsted's experiment.
Okay, but you were talking about the proof that electrons move in a wire. So that would be it.
It's a theory, okay?
Well, it's no longer
It's a
theory there. It's a proof.
Based
it's no longer a theory there. It's a proof.
Not at this stage of electrodynamics that I'm talking about.
Well, maybe not, but the proof is there.
You're trying to confuse the issue, which is what everybody does along here. Okay, now what was it that Faraday did? Okay, supposedly Ørsted generated a magnetic field from a, quote, current. And this current is this hypothetical thing that's supposed to be flowing from the plus terminal to the minus terminal, right? So what did Faraday do? Faraday supposedly showed that he could generate a current from a magnetic field. That would be the inverse.
Right,
okay.
Got it.
But what was it actually that was measured? There was no measure of any motion of electrons. What was measured was that when a magnet was brought up to a loop of wire, there was a device called a galvanometer that uses a magnetic field to move a compass needle. Okay, so when this magnet moved up to a loop of wire, this magnetic field was created in the galvanometer that caused a compass needle to move. So the only thing that happened there was magnetism in motion created magnetism in the loop of wire that was detected in another magnetic detecting device. Nothing about electrons in motion has anything to do with that experiment.
I don't agree with that last statement, but everything else was right on. Because I could say, look, what am I hearing?
Where are the electrons? Where did you detect electrons in that experiment?
So, Harry, we know better now, so why discuss what we didn't know back in the Stone Ages? What's the significance of that?
Well, you're creating red herring. The bottom line is that a moving magnet approaching a loop of wire, a conducting loop of wire, created a detectable magnetic field in a galvanometer detecting device. And so it was said that the magnet moving towards the wire created a current. Well, there's no measure of any charges in motion. The only thing that was measured was a magnetic field that caused the needle in the galvanometer to move, and that's purely nothing but magnetism. So there's no current, no proof of any current involved in anywhere in this experiment.
Okay, that's fine. And then we go beyond that and hypothesize and have a theory of the cause, and I think that's what Maxwell's electrodynamics is, which I have a lot of problems with.
Well, that theory assumes that there's a thing called current, which is charge in motion, because that's the assumption that the originally went back to the 18th century with Franklin, okay? And he said that, well, electricity was too much in the plus and too little in the minus. And so when you connected the plus to the minus, whatever it was that electricity is, you had too much of it in the plus, and so it went from the plus to the minus. And they said, okay, when that happens, you have a current of electricity. They have no idea what this electricity is, but that was their hypothesis.
And that's where I'm continuing as well with that hypothesis that it is a magnetic field. The cause of that, though perhaps experimentally we don't know, the hypothesis is that it's generated by a charge in motion. And that's a hypothesis.
That's all it is.
Well, I can see that. That's fine. And now if we use that
And then
hypothesis...
Einstein comes along. Okay, now let me talk about something else here, okay, which is another problem. When Faraday did his experiments on electromagnetic induction, and if you go and you look at Faraday's book, it's extremely confusing because he was able to generate a current from a rotating disk in a magnetic field. And
Right.
But there's this other thing that came up, which is called unipolar induction. Okay, and there's this issue about the generation of electricity in a moving disk, and this created what's called the unipolar induction controversy. Okay, and that's never been resolved. Okay, that's never been resolved. How this unipolar induction works is still a controversy in science and was never resolved. So what we have is the whole phenomenon of induction, okay, induction of electricity due to a magnetic field is basically a lot of theory that they claim, fits the facts. They've sort of adjusted things to fit to the special theory of relativity, but you still have this unipolar induction problem, which is not fully explained. Now, in addition to that, after all this with Einstein, okay, Einstein was in 1905, about this time they discovered superconductivity. Now, what happens in superconductivity is when you bring a magnetic field up to a superconducting loop, okay, all right, it turns out that you can induce a perpetual current in that loop. Okay, how is that possible? That's not really explained by the theory of electrodynamics or electromagnetism as we know it. It's not a very satisfactory phenomenon. We also know that they suspend magnets. I'm sure you've seen this experiment where they put these super magnets over superconducting materials and it's suspended in midair. Okay, why would that happen? That violates Faraday's law that says that the magnet has to be moving in order to induce the current. But that's not the case. The magnet just sits there and doesn't move.
Right. There's a couple of responses, if I may. The issue of the unipolar...
So what does people have to say about that? Is Faraday's law wrong?
A couple of comments
you guys
there,
still
Harry.
out there? But guys, I've kind of lost control of the window for easy talks here. So
okay.
Can you guys hear me?
Something's funny is going on.
Okay,
right
Harry.
Now my screen is frozen. I can hear you, Harry, but I no longer have control of the screen. What are you guys seeing on the screen?
Yeah.
Hi,
Blank.
Franklin, I only see a white screen. I don't see
Blank.
anything.
Is anyone else here on the conference?
Hello?
Because I've got my easy talk is not responding, so this is not good.
Hello, this is Bob Gray. Can you hear me?
Yes.
You're saying blank. I'm not sharing because as soon as I stop sharing, then something really weird happens.
Yeah. Okay, Harry.
Okay, we're still talking.
I got a screen with
a camera with a slash through it.
Yeah, I think it's trying to catch up.
Okay. Harry, a couple of comments.
Okay, well, we can keep going here, but I might have to restart the conference if it doesn't clear up.
I thought the unipolar Faraday disk motor, whatever you want to call it.
I think we've kind of gone really in a kind of a wide circle here. So I know, Harry, you're just trying to make the point that electrons don't constitute current. I know that's kind of a pet theory of yours. I disagree with that. I think most people would.
I never said that.
No?
I didn't say that. I didn't say that once during this whole discussion.
I'd like to respond.
It all seemed to be going that direction. Okay?
I'd like to respond to some of Harry's comments, please.
Yeah, none of this has been proven a flow of electrons.
Okay, can I respond to some of Harry's
comments?
comments?
Back to Bob's point, it's like, what was Einstein saying about the relative motion between a magnet and a wire.
Hello, can anyone hear me? This is Bob Gray.
So Bob's point seemed to be that electrodynamics would seem...
I hear you, Bob.
I'd like to then respond to some of your comments. One is I thought that the unipolar generator
is like is your point
hello, Franklin.
That basically electrodynamics is wrong. I mean, I've heard you say that it's wrong because they only consider the motion, the velocity of the charge in the wire. Although, like I said, I can hear you guys. What was the question?
Well, the delay must be really bad. I'm trying to respond. I am talking. I'm trying to respond to Harry's comment.
I lost control of my controls here, so.
Okay, I'll try it again. For the unipolar...
You guys want to restart the conference here because I have lost control. Which means I'm going to stop the conference and then restart it immediately. So when the conference drops, you need to all come back in. You guys understand that? Say yes.
Yes.
Okay, we're going to try. I got to kill the conference.
Anybody?
Can you hear me?
I can hear you. So we got 9 participants still here. And I have control of the Easy Talks once again. Okay. So, Bob, were you trying to say something? I'm going to have to unmute you.
Yes. I was trying to respond to Harry's comments, most of which I agreed on, but I'm trying to understand why, Harry, you say that the unipolar induction machine or Faraday's disk is still not settled. I've read several things by, for example, J.P. Wesley, who's done experimentation in theoretical analysis that seem to really explain that quite thoroughly. Professor Assis has also written a paper on Weber's approach to the Faraday disk, and that seems to match up with all the experiments. Is there a particular aspect that has not been satisfactorily explained?
Well, my answer to that is people are still publishing papers claiming they've solved it. So I'm assuming that if people are still publishing and arguing about it, that it's still a matter of controversy. Obviously, you know, you can believe what Wesley says, and you know, I'm not particularly persuaded by his argument. I'm not particularly persuaded by any of the arguments of people who claim to have solved it. So, and people continue to argue about it, and so that's the basis of my claim.
Okay, that's interesting. The other comment I had was Assis recently published a paper on a Weber interpretation of superconductivity. I have not read that paper, but I just wanted to throw it out to you if you were in particular interested in that aspect. It is out on his website, a Weber interpretation of superconductivity.
Yeah, the point here is, I just want to make a little point here, that Weber theory is sort of a minority viewpoint that is not really accepted by official physics. And I think you know what I mean by official physics. That's what appears in the textbooks. And if you disagree, you know, they may let you publish a paper in an obscure symposium, but you know, it's not going to do the textbooks that are presented to college students. Okay, so the Weber theory is, now my point of theory goes back to the idea that there are two forms of electricity, okay, which was, as I discussed, the Franklin theory, which is electricity flows from plus to minus. The Weber theory is an extension of the Simmer theory, which is that it goes from plus to minus and minus to plus simultaneously. So there are two kinds of electric current. And that has sort of maintained itself in the Weber theory. But that's not really, considered by the official physics people as something that they teach in school or anything like that.
Yes, I agree, and I am unfortunately well aware of that. I have dived deeply into Weber theory and think that it is probably the best for classical electrodynamics. That's a personal opinion. I have hooked that up with Maxwell's theory and find that the difference between the two is not so far different as people in the past have thought. The main difference between the Weber theory and Maxwell's theory is this definition of current density. If you put in the velocity of the test charge particle, you come a long way to getting Weber electrodynamics. And I know Weber electrodynamics has not been thought of as a field theory in the past. I have the equations now, and I think I did a presentation here at one point that showed that Weber's theory is just as much of a field theory as Maxwell's. Anyway, it's to me a very interesting area of research.
Okay, now back to the comment about Einstein. Einstein isn't really criticizing Weber, and I don't think it would be interpreted as saying that he's saying anything about Weber. But and there's some controversy about what he's really saying, but the general idea seems to be that he's criticizing the theory that was at that time being taught in textbooks. So, and some people say the textbook is the Abraham textbook. And there was, I can't remember the guy's name. Abraham revised a textbook that was done by a guy before him. Do you remember his name?
I don't off the top. I am aware of the Abraham, but I don't know what preceded it.
Well, most people believe that Einstein's criticizing that textbook version, which is, I do believe, Maxwell's electrodynamics, or an interpretation of Maxwell's electrodynamics, or more actually electrodynamics and electromagnetism kind of synonymous at this time.
Right. Okay.
Well, I have this wiki page, what is saying the inconsistency of Newtonian mechanics with Maxwell's equations of electromagnetism and a lack of experimental confirmation for the hypothesized luminiferous ether led to the development of special relativity, which corrects mechanics to handle situations involving motions at a significant fraction
of
the
let me
light.
comment on that. The basic thesis is that in the official version and I can't remember the guy's name, that the Abraham textbook, it's the guy wrote a textbook, and then Abraham came along later and revised it, and then that book has been revised by Becker, so some people refer to it as Abraham Becker. But by the time it got around to Becker, they had massaged it so that special relativity was taken into account in the textbook, and that was a fairly later version of the textbook. But in this book, the thesis was when a magnet moved through the ether, there was an electric field generated in the ether. and that electric field that was generated in the ether induced a current in the loop. Okay. But when the loop moved towards the magnet, it's just that the magnetic field was induced in the loop by the motion of the loop moving towards the magnet. I hope I've got the two cases correct. And Einstein said, well, this doesn't really make any sense because we have an asymmetry. And the asymmetry arises by virtue of the thesis that there is an electric field generated in the ether when a magnet moves relative to the ether.
Yeah, maybe just that theory was wrong.
Yeah.
Well, the textbooks have been revised to correct that because they banished the ether, and so there's no mention of the ether, and so that's not a problem anymore because the ether doesn't exist in electromagnetic theory.
Well, I would say that the whole idea that you have an electromagnetic field being generated by a magnet in motion is just crazy because that's just wrong.
I had a
Magnets don't generate electromagnetic fields. Only charges do.
A thought based on my reading of Weber, and at the time where there is no fields but only charges in motion, the thought is, can you replace a magnet, a permanent magnet, with a current loop and do the two generate exactly the same kind of magnetic field or B field?
Well, that's a good question. I've always wondered about that.
I don't really know the answer.
I mean, they kind of look like they do the same thing.
It's pretty clear to me that you can't really maintain that a permanent magnet is created by a current.
Well, it doesn't look that way. I mean, there's ways of coming up with hypotheses to explain that.
I'd love, Harry, for you to.
Well, I mean,
I'd love to expand. I'd love to have you expand on that either here or by email with me, so I can kind of understand that that kind of point of view, because I don't get that point of view at the moment.
Well, where's the current? Where's the current?
The current is in the spin of the electron, the magnetic moment of the electron. The magnetic moment. Okay.
That has been investigated, but pretty much ruled out that that couldn't be due to the anything on the individual atomic level. Because if that were the case, then there should be a lot more ferromagnetic materials than just the three that we find in the on the periodic table, which is like iron and nickel and well, there's in one of the cobalt, I think. Because you see, that's the main problem with that theory is like if there are a lot of other atoms which are very similar to iron as far as structure goes, and they're not ferromagnetic. So
it requires free electrons to be there to be able to be moved.
Yeah, and there's plenty of free electrons in all the other atoms around the three known ferromagnetic elements.
Now they're all captured within the molecules or within the structure of the atom itself.
I'm just saying that any explanation of ferromagnetism at the atomic level just doesn't wash out, because there's nothing about those three elements that would restrict that behavior to just those three elements.
But this is why I kind of asked the question, what's the difference between the magnetic field generated by a permanent magnet and a magnetic field generated by a current-carrying loop of wire? Is there a fundamental physical difference between those? The source may be different, but the result, that magnetic field, is there a difference?
No, there's no difference. The only difference is that the electrical loop that the current is flowing through is much smaller if it's just around the atom.
And from that point of view, then all magnetic phenomena is due to charge and motion.
That is a hypothesis.
That's an hypothesis again.
Yeah, and
I agree.
Not so far consistent with measurements.
Or as far as we know, it could be something entirely different.
The point is basically when you measure current When people measure current, they're really measuring either magnetic field or voltage drop across a resistance.
Yep, but I could also say when you measure sound waves, you're not measuring the vibration of the vocal cords, you're measuring the wave at the detector. But I want to know what the source of that wave is, and I hypothesize that it's the vocal cords. And same with magnetism. You measure the magnetic field, but what's the source of that? And the hypothesis, yes, hypothesis, is that it's charge and motion. What the motion is, I don't know.
Now,
All right, let's go back to what Cornelius said. Excuse me, I'd like to go back to what Cornelius said earlier about
the point of whether,
the point being this.
Go ahead, Harry.
Cornelius said that the point is not the charge, it's the field that's the charge. You remember that discussion?
Yes,
okay.
And I love it. I love it.
It's an hypothesis that there's something that exists inside of a, quote, charged particle called charge that creates an electric field. But we don't measure any such thing as charge. We only detect it because we detect the field. So, in effect, basically, it's an hypothesis that something called charge creates an electric field. There's no proof that there is any such thing.
It's a hypothesis.
Well, when we have a singular electron hitting a silicon detector, it makes a specific spot at a finite sized spot at a finite amount of time. So in my mind, that is very good evidence for an electron being a particulate matter.
Which is the focal point and the most.
We're not talking about that, Franklin. We're not talking about that. We're not talking about whether electrons exist or not. We're talking about what charge is.
Yes, well, I've explained that charge is, in fact, an electromagnetic wave being generated from an electron at its resonant frequency. That's one possible hypothesis.
I rather like Bill Lucas's point of view, which I think might be close to Cornelius, is that it's the field, and the field somehow ties itself into a knot. It goes down. When it gets small enough, we can detect it as a quote-unquote particle. But the charged particle doesn't create the field. It's the field that creates the particle.
Yes, and I would completely disagree with that one. That is totally wrong in my opinion.
I would agree with the last statement, Bob, that the field is the particle. As far as Bill Lucas is, he still goes farther and has particles are made of charged fibers, individual one-third fibers, according to what I've heard understood. And that means that charge is an inherent characteristic of a fiber. And unless you define what the fiber is, you're still having a charge of some kind that's of an indeterminate source. So I don't necessarily agree with Bill Lucas's finite definition of it, but I do agree that the field culminates. It's the shape of the field and the strength of the field that defines the electron.
Yeah, I haven't gotten that. I haven't gotten that far with Bill Lucas's things.
Yeah, it's not just a charge field. There also has to have a mass, because there's no such thing as an electron without mass.
And all of those theories have this chicken and the egg problem that you're kind of relating it to some mystical field, which you still can't explain.
I explained it
perfectly
fine.
That's why I think my explanation is the only one that explains the physical phenomenon in terms of things that we actually recognize. So if we recognize a charge field in terms of electromagnetic waves, then we don't have this chicken and the egg problem. We know what it is.
We don't have a chicken and an egg problem anyway, because you need to have waves to go between your particles in order for the particles to communicate to each other, and you have to describe what those waves are moving through. I simply make it just, it is waves moving through the ether, and the ether is a continuous tensionable field.
And that's the chicken in your egg. It's like you can't explain that.
I don't need to explain that.
You do need to explain that. You absolutely need to explain that. You cannot have that as a postulate.
I just did explain it. It's a tensionable field without particles. It's a continuum.
Yeah, and that's a humongous postulate. You might as well have said they're fairy tales. There's little green men who propagate the field.
No fairy tales, no little green men, no parts. Just a continuous field, a tensionable field. Something that tension can move through. That's it. And you
can't explain that. That's a very big problem.
And you do not require particles to define tension. You require particles to be able to visualize tension.
Yes, you absolutely need particles to define tension in every mechanical way. It requires particles.
Between particles, there is an attraction. The attraction is the only thing we sense. The only thing we sense is the energy between these patterns. These patterns are nothing more than patterns of tension in motion. Period.
Too many unexplained things.
Nothing unexplained.
That's a hell of a lot of postulates.
Simple tension and motion in a continuous, elastic, tensionable field. Period. No parts to the field. It's tensionable.
Well, that makes no logical sense. Sorry. There cannot be tension without particles.
That's not true. Because there cannot.
Well, that's your opinion. He's got his hypothesis.
There cannot be.
And that's also
I think it's a reasonable hypothesis.
There cannot be tension between particles without something between the particles, and that is tension, a tension field, a tensionable.
And there cannot be tension without there being particles between the two particles that you're talking about.
There can be, because particles are just conglomerate focus points of tension, just like.
I have seen no examples of that in reality, right?
Everywhere you look, you see particles. I look at a clear water pond.
Yeah, you see particles, and that's because they're hard little balls.
I look at a clear water pond, and I look at the tension on the surface of the water pond, and a raindrop hits it, and I see the tension spread, the effects of the tension spread. And what I see when it hits something else on the pond is the effects of the tension moving that something. And I see
all of those waves being made out of particles.
It's because you can see them. It's because they're on that level. It's because they're on that level, but the ether is not on the visible level, because the ether is the conduit of light. It is not the...
You're building a castle in the sky.
Yeah, and it is built, and it works.
That's right. There's still a castle in the sky.
There is a...
well, the bottom line is...
Go ahead, Harry.
I was just going to say, the bottom line is official physics is based on particles and void, and that really doesn't work too well. The void being a nothing, and so they kind of have to invent a particle to be the field, and they're chicken and egg. It's the same thing.
Official physics is an idealization of energy packets to make calculations simplified, because quantization happens in particles that are composed of fields, because fields that are made of resonant wave patterns can only change their amplitude and gain at a consistent single wavelength at a time value, or they no longer exist. They no longer maintain their resonance. You can't change a resonance without changing it one resonant field, without changing an entire cycle at a time. And that's why we have quantization that makes it look like a particle changed by a specific amount.
Yep, I agree. Cornelius, do you know the researcher David Zaretsky? Have you read any of his work?
I don't get my information from reading that much. I don't.
Oh, okay.
I get my reality from my ideas, my visualizations, from observations and experiments.
Okay,
it's just very little reading.
This David Zaretsky guy has a lot of papers out on derivation of classical electrodynamics and particle physics, etc., all from an elastic theory. He's taking regular mechanics, theory of elasticity, and deriving Maxwell's equations, and then he goes on and on and on into particle physics, etc. It's really quite an interesting approach. Everything from the elasticity theory of classical mechanics.
Well, there are many people doing this. That's not the point. I mean, Milo Wolf was my first encounter with the concept, actually, but he had problems. More recently, we got Jeff Yee, who's promoting this type of thing, but he hasn't got a real good model that defines the transition between longitudinal transverse waves. There's Hans van Loonen, who has somewhat the concept, although he has basically what he calls, his particles basically originate at the focal point by some kind of mysterious oscillation or stimulation. In my view, basically particles are the focal point. That's not where the energy originates from. That's where the energy is consolidated or focused to, and particles can basically transform longitudinal gravitational energy into transverse light energy.
Yeah. I also looked at Milo Wolf's work, and I enjoyed a lot of his, or what I read of his, because he had a couple of books out, but I couldn't understand how he gets an incoming wave. He has an outgoing wave from a body, but also an incoming wave, and that sets up a standing wave. I couldn't figure out how, if the body is in motion and moving, how it can always be focused on where the body is going to be, the incoming wave.
Interestingly enough,
For me, that's another topic,
Right, and I don't have the outgoing wave. I simply have an incoming wave. Any outgoing energy is in the form of gravity and or the form of light. So, incoming waves only. Matter absorbs energy, and it gets too much energy, then it will expel it as light or gravity. Actually,
okay, so guys, we're getting towards the.
That's interesting.
We're getting towards the end of the time here, so I've just been trying to work up a little summary of our discussion here. So if I forget anything, let me know. But so we started off the discussion here about Henri Poincaré and whether Bill Lucas had a book that he couldn't get out of the library. So we did a little research on our own. Really don't think that we could really find anything obvious, and we're just going to have to wait for Bill to see whether he can dig up the name of that actual thing. Then Bob Gray brought up this discussion here on something mentioned in Einstein's 1905 paper about electrodynamics, and that there should be this symmetry from electrodynamics. And excuse my spelling here, I seem to be misspelling everything all over the place. Thank goodness for spell correctors. And so, but the problem being brought up here is that conventional electrodynamics only takes into account the velocity of the test charge, and that the definition of the current is generally wrong. And that we have to take into account the velocity of the source as well as the test. But then the question was brought up, where's the velocity of the source in the magnetic field? And then we have permanent magnets which have no clear current loop in them. And so we have this question of, well, is the magnetic field the same as those created in electric loops or permanent magnets? And that's still an area of speculation. I mean, one comment I did want to bring up, it is possible that, like for example, atom could have an inherent magnetic field which is not due to a current loop. That's a possible hypothesis, because all you need to do to make a large magnetic field is just to put a whole bunch of small ones together, right? So if it were possible somehow for an atom or some conglomeration or a crystal or whatnot to generate any kind of small magnetic field, that could generate the whole observed magnetic field in a permanent magnet. So it may have to do with current loops, or maybe not, but that's all it takes. And then we got into this whole question about how Faraday's law works, because this is this V cross B, which is velocity cross magnetic field, and where's the velocity in that? And then finally we got into discussion about particles. Is the particle its field? Is the field the particle? Is the particle made of fields, or is the particle a solid little ball? And there are lots of opinions on that. So we got a little bit into that. So I think there's a very interesting discussion today. Now, I had originally scheduled to talk something about gravity, and so we'll save that for next week. But as a teaser, so here are my graphs here showing that the mass of the Earth appears to decrease depending on which satellite you look at, and the further out you get, it's less. And same with the planetary orbits. That you measure what the mass of the sun is according to the orbits of the planets. They have this weird pattern. So, but I think we will save that for another time. So, Bob, did I get all that right?
No, but it's fine.
Okay.
It's okay. It's a good summary, I suppose. Yeah.
All right. Well, we don't really make any conclusions here or force anybody to believe anything. We're just here to talk about stuff. So that will do it for this week's episode. I thank you for everyone for participating, and hopefully see you next week.